Hi guys, so in this video we're going to be talking about topic 13.5, optimization. And we're going to do a few examples, and basically they're all very similar. The difficulty in optimization is actually finding the equation we need to use, because after we find the equation, all we have to do is find the first derivative equal to 0, solve for x, and then verify if that is actually a maximum or a minimum, depending on the case and what they request. So let's look at example 13.25. And it says, find the maximum area of a rectangle inscribed in an isosceles right-angled triangle whose hypotenuse is 20 centimeters long. So it's a rectangle, as we can see here, and it's inscribed in this isosceles right-angled triangle. Um, so there's a few things here. First of all, they give us the length of the hypotenuse, which is 27 centimeters. We have that. Also, we know that this angle here and this angle must necessarily be 45 degrees. Now, why is that? Because if it's isosceles and right, we know that this is 90 degrees here. Therefore, the other two angles have to be 45. Same situation with this triangle in the corner, the bottom right corner, because this is definitely right, of course, since this is a rectangle, then we know that this is 45. But because this is 45 and this is 45, then this side and this side are equal. And then if the length of the rectangle is x, then we know that what we have left has to be x minus 20. So each side would be that divided by 2, right? If we know that the remaining length of the triangle after subtracting x, right? If we have 20 minus x is what's going to be remaining, then dividing that by 2 is going to give us 10 minus x halves as each one of these lengths, this length and this length. But again, because it's isosceles, then this side is the same. So that means that we have everything in terms of x in order to solve this problem. And that is really the basic difficulty in optimization, making sure you can get a formula in terms of x that then you can just derive. So the area of the rectangle in terms of x would then be simply x times 10 minus x halves, and then this is going to be x 10x minus x squared over 2. And then all we have to do is find the derivative and equal to 0, right? So the derivative of a would then be simply 10 minus x, as you can see. Equal this to 0, and x would be 10. So theoretically, this would be the maximum. And it's easy to see because if you look at this equation we have here, it's obviously an inverted parabola. But just to get into the habit of it, you will have to test always in these problems the extremes in the domain. Now notice that x could be any value theoretically, right? I mean, logically no, but theoretically, and depending, and you might as well get used to this. X has to be less than 20, less than or equal to 20, but greater than or equal to 0. Now you would say that's not logical, but just get used to that in order to plug in always those extreme values in the function, just to verify that this is actually a maximum. And this is easy to see that it is so, because if you plug in 0 in the area function, a of 0 will give you 0, and a of 20 will also give you 0. Therefore, this is definitely a maximum. So the area is maximum when x equals 20. And if we plug in, it says find the maximum area. The maximum area would then just be plugging in 10 here. So it would be 10 times 10, right? The maximum area is when x equals 10. So 10 times 10 minus 10 squared divided by 2. So this is going to be 100 minus 50, which is 50 centimeters squared. Okay, so now we are in example 13.26, and it says 2 vertical posts with heights of 7 meters and 13 meters are secured by a rope going from the top of one post to a point on the ground that is between the posts. So that's R right here. It says the distance between the two posts is 25 meters. Where should the point at which the rope touches the ground be located so that the least amount of rope is used? So they want to minimize the length of A plus B, right? That's what they want. They want us to find a minimum for A plus B. But of course, we don't want it in terms of A plus B. We want it in terms of X. And we have all the information because if we call this X, then we can call this side 25 minus X. And we also have the height. So with the Pythagorean theorem, we can easily find equations for A and B. So notice that A would simply equal the square root of 7 squared, well, let's start with X, of X squared plus 7 squared, right? Which would be 49. And then B, the length B, would be equal to 25 minus X squared plus 13 squared, which is 169. 169, and we can simplify this or expand it, and we can make this would be X squared minus 50X plus 625 plus 169. Of course, square root of all this, and this is going to end up being equal to the square root of X squared minus 50X plus 794. Okay, so that's A and B. So obviously the area, which we'll call A of X as a function, so area as a function of X would then be equal to the square root of X squared plus 49 plus the square root of X squared minus 50X plus 794. Okay, so we need to differentiate this here, right? We need to differentiate the area in order to find, oh, this is not an area, this is a length, excuse me. So let's erase A. It's a length L. So L, we need to find the minimum for L, right? The length that is obtained from adding A and B, A and B. Okay, so in order to find the derivative of that, remember that we're probably going to have to do here, and not probably, but we have to do the chain rule and consider the square root as 1/2. Okay, so we could rewrite this or write the derivative as being equal to 1/2 times the inside, right? X squared plus 49 to the power of negative 1/2 times the derivative of the inside, so 2x, plus 1/2 x squared minus 50x plus 794 to the power of negative 1/2, and let's not forget to multiply by the inside, right? So this multiplied by 2x minus 50. Okay, then we can fix this up a little bit. Notice that we can simplify a few things. We can cancel out this divided by 2, and then this is multiplying here. So I can simplify this by making this x minus 25 here and getting rid of that bottom 2. So if we rewrite this, we can write this as x over square root of x squared plus 49 plus x minus 25 over the square root of x squared minus 50x plus 794. Okay, so now we have to equal this to 0 and then solve for x. The thing here is that because we have two different fractions, we have to add these fractions before we actually are able to solve this equation, because then the bottom part wouldn't matter and we would only have to solve for the top, right? But notice that in reality we would get something like x times square root of x squared minus 50x plus 794, right? I'm going to cross multiply, plus x minus 25 times the square root of x squared plus 49. And this would then be over this multiplied. But I'm not even going to bother writing that. In fact, I'm going to go to a next blank page and continue with this in the next slide. Okay, so here we are in the next slide, and I have already written down the derivative and equaling it to 0. So I said before that this doesn't really matter, right? Because we only have to solve for this part. So notice that we can rearrange this and rewrite it as x times square root of x squared minus 50x plus 794 is equal to negative x minus 25 times the square root of x squared plus 49. So what we do next is that we're going to square both sides in order to get rid of the square roots. If we do this, we're going to get x squared times, and the expression inside the square root, x squared minus 50x plus 794 will be equal to x minus 25 squared. And notice that I got rid of the negative because this is going to be positive, right? Times x squared plus 49. And then if you multiply and expand all this and then rearrange and all that, you guys know how to do all that, you're going to get 120x squared plus 2,450x minus 30,625 is equals 0. Then we can factor out a 5 and just do inspection, and you're going to get 4x minus 35 times 6x plus 175. And obviously the solutions for x will be 35 fourths here. And this one will be negative, therefore we're not interested in the solution for this. So x is equal to 35 fourths. Now here we have to actually test the values 0 and 25 as the extremes of the domain. So we have to test with L of 0, because that might give us the shortest length for the wire, right? If we just put it from one post to the other, to the bottom of the other one. And this will give you, if you plug it in the original length equation, it's going to give you 35.18. If you plug in 35 fourths, it's going to give you 32.02 approximately. And then if you plug in 25, you're going to get 38.96. So this clearly here is the lowest value, the lowest outcome, at least for the length. So just so we're clear, we found that the shortest length was when x equals 35 fourths. 35 fourths. And we got that the shortest length would be equal to L of 35 fourths was equal to 32.02 meters. But x is 35 fourths. That means then that this distance would be 35 fourths of a meter, right? In other words, at what distance would R be? It says where, the question was, where should the point at which the rope touches the ground be located so the least amount of rope is used? And if we think about the distance from Q, or from Q to R, then that distance would have to equal, that length would have to equal 8.75 meters. All right, so this will be the last example that we'll cover on this video, and it's example 13.27. And it says, a 4-meter length of wire is to be used to form a square and a circle. So they want to form a square and a circle. How much of the wire should be used to make the square, and how much should be used to make the circle in order to enclose the greatest area? So they want us to maximize the areas. Now notice that we can think about the areas as being equal to x squared in the case of the square, and we have to add the area of the circle, which would be pi r squared. Okay, so here we have a difficulty, and the difficulty is that we have two variables. So we always want to do these optimization problems using x as the only variable. So that means that we have to change r to x. Luckily, we have another equation that we can take advantage of, which is the total length, or based on the total length of the wire, because notice that if the total length of the wire is 4 meters, that means that 4x, which is the total perimeter of the square plus circumference. In this case, remember that the circumference formula is 2 pi r, has to be 4. Okay, so basically all we have to do is rearrange and solve for r. And that's something you guys can do on your own. In the end, you're going to get that r is equal to 2 times 1 minus x over pi. And we can substitute that back in here. So let's do that. I'm going to erase r squared, and instead of r squared, I'm going to now use this expression in terms of x. So we're going to get 2 times 1 minus x over pi, and all of this squared. But this is something that can be simplified further. We can try to simplify this as much as we can in order to make it easier to then find the derivative. Okay, then we have that the area in terms of x would then equal x squared plus pi times 4 times 1 minus 2x plus x squared over pi squared. And notice that we can cancel out one of these pi's with this pi. And then we can rewrite this. Let's just rewrite it as, let's write it as pi x squared plus 4 minus 8x plus 4x squared, and all this times 1 over pi. Okay, then notice that we have similar terms like x squared and x squared, so we might as well put that together. So we have 1 over pi times, and we should use a square parenthesis here, times pi plus 4x squared, and let's rearrange it, minus 8x plus 4. Okay, so this looks more organized, and this is a lot easier to differentiate. So that's what we're going to do next. We're going to find the derivative of the formula. And notice that for this, 1 over pi is a constant, so we don't really have to worry too much about that. So this is going to be 1 over pi, and then we send the 2 to multiply, so we're going to get 2 pi plus 4 times x minus 8. Okay, and then we need a maximum. So we have to equal this to 0 and solve for x. So notice that we can get rid of this, right, because this equals 0. And then we will have that, that 2 times pi plus 4 times x is equal to 8. And then rearranging, we're going to get that x is equal to 4 over pi plus 4. And this, if you plug it in the calculator, is approximately 0.5601. Okay, so now the range of values for x is going to be 0 and 1, right? Because if x is 1, you would use all 4 meters on the perimeter of the square and nothing for the circle. And then if x is 0, we would use all the wire on the circle, because remember that the area of the circle could be just in terms of r, and x could be 0 easily. Notice that if you plug in 0 here, you would have an area as well. So we have to test for those values, right? So if you test for 0 in the area formula, you're going to get approximately 1.273. If you test for the value we found, which is somewhere in the middle, 0.5601, you are going to get approximately the same, 0.5601. And then we have to plug in the maximum, which is when x equals 1. So for 1, we're also going to get 1. What that means is that the maximum area occurs when x is equal to 0. So if x equals to 0, that means that all the wire is going to be used on the circle.